In last class, we talked about a very simple toy example for fuzzy logic. But the fuzzy logic, if used properly, can be used to control robots. As a matter of fact, when I worked on Bell 609 project, we used fuzzy logic for sensor fusion, and it worked very well. And that code is still, it was certified, and that code is still used in Bell 609 air data altitude heading reference system. And fuzzy logic, depending upon how you look at it, can be considered as some universal function approximator. That is where it is similar to some machine learning neural network type of architecture. You can couple fuzzy logic with some type of a neural network and construct a neuro-fuzzy type of system. So the idea is, again, in the fuzzy logic, is how do we take the human knowledge and human experience and translate that into some algorithm that machine can understand. For an example, humans can understand what I mean by pretty close. Machines don't. So how do we take these ambiguous adjectives and convert that into something that is machine interpretable, so we can perform some computations, come up with some decisions, and sort of add the knowledge representation to the machine. So what I want to do in today's class is I want to take a very simple example, and then I will try to solve it using a non-fuzzy approach, and then I will try to solve it with the fuzzy approach. Now, if you think about this whole workflow, it may seem complex, but what happens is MATLAB has its own graphical user interface, which is Fuzzy Logic Developer app, Fuzzy Logic Designer app. You can design the fuzzy logic algorithm using that app, then click a button, and that fuzzy logic, the control logic, gets written into a C code. That C code can be programmed into a microcontroller or a Raspberry Pi or any embedded system of your choice, and you can use it. But the basic concepts remain the same. So let me take a very simple example, and then I will show you, if we were to do this, if we were try to achieve this human interpreted knowledge using some type of computer algorithm, how complicated the things get. And then once we incorporate a fuzzy logic, or if we use some simple fuzzy logic algorithm and membership function, how that whole thing gets simplified. So I want to start with a very simple example. Imagine semester is coming to an end. Today is the last class. So say you want to party and you go to a restaurant. And you go to a restaurant, and then basically at the end of your meal, you want to give some tip to the person who is waiting. Now, how would you decide how much tip to provide? Typically, the tip that you provide can vary anywhere between 5% or 15% to 35%, depending upon how good the service was and how good the food was. So food quality and service quality, these are two aspects that determine how much tip that the patron would give at the end of the meal. So let's try to understand the logic behind this. So the problem that I want to pose here is, like, depending upon the food quality and service quality, you will decide the tip. And this tip could vary from 15% all the way to 35%. So which means if the food is excellent, if the service is excellent, say you want to give 35%. If food is very bad, if the service is very bad, then maybe you want to give 15%. But most of the times, food quality of the food and quality of the service would be in between these two extremes. So how do you decide how much tip to provide depending upon, or how much tip to give depending upon the perceived quality of the food and the perceived quality of the service? So let's pose this problem. Now let's try the simple logic. Say the first part, what I want to do is I want to start with a non-fuzzy approach. So it's just basically a simple algorithm wherein I'm not going to use fuzzy logic, fuzzy membership functions. I'm just going to come up with some type of crisp boundaries or crisp rules. So for an example, I'm going to say the tip is always going to be 15% of the total bill, irrespective of the quality of the food, irrespective of quality of the service. So what I want to do is, I want to show how the tip changes. So if I run this section, and this script is actually on the canvas. So imagine if the service quality is 0, which is a pathetic service, and if the service quality is 10, which means outstanding service, no matter what the quality of service is between 0 to 10, my tip is going to be 15%. So I'm having this gradation. So food quality can vary from 0 to 10. Service quality can vary from 0 to 10. So as a first case, for non-fuzzy approach, I'm going to say my tip percentage is always going to be 15%, irrespective of service quality. Now, what I want to do is, I want to add a little bit of sophistication to this algorithm. So I'm going to say the service is going to get rated from the scale of 0 to 10, and I'm going to increase the tip linearly, which means if the service is absolutely pathetic, it will be 5%, but gradually I would linearly change the amount of tip based on the service. So initially the case was no matter quality of the service, tip is same. Now what I'm saying is the quality of service and the tip, they have a linear relationship. The better the quality of the service, higher the tip. So that's why what I did is I came up with this linear interpolation. So I'm going to run this section. Now please observe that now I have this linear variation. Linear variation, when the service quality is 0, my tip is 5%. When the service quality is excellent, the tip is 25%. Now, what I want to do is, this is just irrespective of food quality. So I'm saying the food quality is great and my tip is proportional to the service quality. Now I want to add one more variable to it. So in addition to the service quality, I want to have some dependence on the food quality. So what I'm doing here is, I'm actually adding one more variable, which is the food quality. So what I do is, I'm adding something called as a food quality term F to the tip formula. And what that means is, so my service quality will be on from 0 to 10. My food quality will be from 0 to 10. And finally, I'm going to combine food quality and service quality together and determine the tip. Here, one thing to be understood is I'm weighing food quality and service quality as the same, which means both of them are weighted equally. So what I do there is basically, as you can see on line number 23, I have the tip, which is nothing but the addition of the food quality, which is stands for F, the number F, that could be between 0 and 10, and service quality, which could be between 0 and 10, and then I generate the tip. So if I were to do that, what I want you to understand is here, now the algorithm changes to something like this. So if you see, so now it will, this is the surface. So now you have the food quality that can go on the scale of 0 to 10. You have the service quality that can go from the scale of 0 to 10. And if your food quality is excellent, if your service quality is excellent, clearly you can see that the tip is going to be the maximum. But if it is in between, then clearly the tip would vary somewhere in between 5% and all the way to 25%. But please understand, in this case, the food quality and the service quality, they are equally weighted. Okay. Now, I mean, for some, service is more important than the food quality. So for an example, if you say, for me, I need a prompt service. I want my drinks to be filled immediately. I don't want to be kept waiting. So what I do here is I add a ratio that gives the relative importance between the food quality and the service quality, which means to me, service quality is 80% of has 80% importance, and the food has 20% importance. So what it means is food could be okay, but if the service quality is excellent, then clearly this will the tip is going to be quite high. So I added this ratio. Now, this algorithm I want to show you can be implemented something like, and you are welcome to run this script. This script is on the canvas. So if you, once you run this, you will see it will give you a plot of food, tip, and service. So basically, this tip, I don't know why this is not showing. R is equal to, and we have F already. Oh, it ran on your system? Okay. I don't know why it is not running on my system. Okay. Oh, I basically because I clicked 2 times. Okay. Let's see. So you can see you will get a plot that will actually give you the weightage. So please run this, and then you will see what you get. Now the next part, this is where the things become very complicated. So here, what you want to do is you want to have some type of a gradation. So everyone visualizes or everyone understands or interprets the food differently. Taste is because the food tastes different. Everyone's taste is different. So good for me may not be so good for you. Service quality, maybe you and me have the same perceptions. So what we want to do is to allow for this bias, we don't want to have a crisp demarcation, but we want to have a flat response. So basically the flat response means that 15% tip will give in general, but I want to specify a variation that is dependent on the quality of the service. So what it means is basically I'm implementing something like a piecewise linear approach, which means if the service is somewhere between 3 to 7, it's okay for me. But if the service is beyond 7, 8, 9, 10, then that clearly is a great service. If the service is less than 3, then clearly that's a very bad service. So what I want to do is, in this particular region, 3 to 7, I want sort of the flat response, but that the beginning and at the end, I want the steep response. So which means if someone is rating the service as 9, the tip will be significantly higher compared to someone, if service is rated as 7. So to implement that, you have to add this piecemeal for piecewise linear function. And then what happens is, then you will get a plot. Let me see. So, okay. So you will get this plot that gives you the relationship when you have some type of flat structure here. So you can see this is the initial linear interpolation. And here now, if the service is in between 3 and 7, then I'm gonna give maybe a 15% tip. If the service is great, then I will give more tip. Now, I want to tell you why is this happening. This is happening because I'm trying to encode the human interpretation. Because for humans, service which is in between 3 to 7 is okay, it's same. So whether it is 4, 5, 6 or 7, that level of service to me is the same. As long as the service goes to 7, 8, 9, 10 or 8, 9, 10, that is a significant improvement and I want to reward that. And here, if the service quality is between 1, 2 and 3, that's a very bad service and I want to punish. So what it means is, if I want to encode the human experience into mathematical algorithm, the things start becoming complicated. Now, this is just with the service. So now I want to add a linear dependence on the food service, and then I want to include the quality. So please try to understand that as I do this, the whole thing is going to become quite complicated. So once you run this, you will realize that the whole process becomes super complicated. And this is just for 2 variables. When you have the food quality, when you have the service quality, and the service quality can go from 0 to 10, food quality can go from 0 to 10. Then as you can see, the algorithm that we have to write, sort of the condition statements that we have to write, they become significant. Now imagine, in addition to the food quality, the service quality, you want to add the cleanliness in the restaurant, or if you want to add maybe ease in parking, or maybe if you want to add maybe the selection of wine, or maybe the type of food. So all these attributes make this simple logic for what is simple for human becomes very complicated when we try to give it an algorithm. Everyone understood this? So that is where the fuzzy logic shines. So for an example, if you have multiple inputs and multiple inputs have different gradations, and then basically those gradations are more like what humans feel or what type of adjectives humans use. Once you start encoding that, then fuzzy logic actually is better. So what I want to do is, if you want to do this using fuzzy logic, I want you to just run this fuzzy inference system, FIS, that stands for fuzzy inference system. Tipper is the logic. The whole logic that we talked about is implemented in the tipper. And then I want you to run this code. I want you to run this code. And once you run this code, First, what it will do is, it will tell you the encoded rules. So basically, it will say that there are three types of services. Service could be poor, service could be good, service could be excellent. Food could be rancid, average, and delicious. Now, what I'm doing is, I'm saying, this is very important. If the service is poor and if the food is rancid, if the service is poor and the food is bad, tip is going to be low. If the service is excellent, if the food is delicious, the tip is going to be generous. But the problem is, what happens once we are in this vague section? What do I mean by vague section? If the service is good and the food is rancid, if the service is good and food is delicious, what happens then? So basically, what I have done is I have encoded the human knowledge, so my understanding, my interpretation into a mathematical algorithm. And now what you can do is you can actually look at the, if you look at this, I want you to look at this guy. And it should be generating a plot. Just make sure the plot is generated on your, for some reason it's not generating on my computer.
Professor,
Yeah,
just this 4 lines of code it gave you the rules.
yeah, you just, so basically, just a second. So what I want to do is, I want to just run this code and I will show you. Yeah, so this gives me the whole logic. So which means now you can see, depending upon my interpretation, I can rate the food, I can rate the service, and this logic will automatically give me the tip that needs to be I would like to provide. So this is how the fuzzy logic actually works. Now, what are the implications of this? This is very easy because you have food and service, only two variables, and tip is the output. But you can have multiple inputs, you can have multiple outputs, and you can define the relationship in between. The important part of this is, after you are done with this control logic, what you can do is you can go to this MATLAB code and export this whole logic into a C code that can be burned on, or you can that can be converted into a hex code, and you can flash a microcontroller that would implement this fuzzy logic. Now, what I want to do is, I want you to look at this MATLAB app, which is Fuzzy Logic Designer, and that actually is visualization of this. So this is how, and I'm going to go step by step, and then I will actually show you how to design this using the MATLAB Fuzzy Logic toolbox. So first, what I want to do is, I want you to understand that there are two types of inputs. One is a service, other one is the quality of the food. And service has sort of three groups. So service could be bad, good, and excellent. Also, same thing happens with the quality of the food. Quality of the food could be rancid, quality of the food could be okay, and quality of the food could be excellent. So what I want you to do is, I want you to double click on service. Now, as soon as you double click on service, please understand that this membership function is poor, good, excellent. And I'm going to use some type of a Gaussian membership function, but you can change the membership function to maybe a linear. So trapezoidal. Can you see that now this function has become trapezoidal? You can use triangular. You can use the Gaussian that we already used. So you can select these individual membership functions with different type of variation. Now, what dictates the shape of these membership functions? Shape of this membership function, believe it or not, is like how I feel. So for example, if I want to use a triangular membership function, which means I'm very rigid, okay, either this way or that way, or and in between. If I'm using sort of a Gaussian, as you can see, the edges are smoothened, which means, okay, it's not that great, but that's okay. If it is little bit less than that, that's okay too. So there is no sharp decline in my perception. So this is how it is encoded. Same thing with good and same thing with excellent. So I want you for one thing, that try these membership functions. There are different membership functions that kind of gives you a tool to encode your feelings or encode your perception or the encode your knowledge, like how you feel about certain things. So then if you look at, so you can have the first membership function, which is poor. So what this tells me is if the service is 0, is definitely poor. If the service is 1, it is less poor, but gradually at when the service is 4, that means my poor is 0, and then my good, I want you to see, good is about 0.8, something like that. So if my service is 5, that means that service has 0 poor component, 0 excellent component, and maximum good component. So basically, this is the gradation. You can select different membership functions and then actually add the boundaries here. Can you see the parameters? Parameters are indicative of boundaries where what it is. So 1.5 and 5. So these are the boundaries. Then what you can do is you can look at the food quality. The food quality, I'm very strict about the food quality. So which means it could, if the food quality is less than 2, it's rancid, and between 2 and 3, it's okay. And then in between 3 to 7, to me, it's all the same. Whether the food quality is 3, 4, 5, 6, 7, that's okay. But as soon as the food quality goes beyond 7, then basically I think, food is really good. And then I want to reward that. So as you can see that these membership function is indicative of rancid. In between, I don't care much. And if the food goes beyond 7, yeah, it's delicious. And you can set up these membership functions, and you can also set up the boundaries. So you are welcome to change these boundaries and then see how that the whole thing changes. And you can change the different types of functions. Then finally, what you have is you have this human knowledge that is encoded. So these are the rules that I write. How do I write these rules? These rules are written using something called as the Boolean algebra. So the Boolean algebra means it could be and, it could be or, it could be not. So basically, this is the Boolean logic that is using the service and food as an input. So as you can see, the logic that I have written here is if the service is poor or the food is rancid, then the tip is cheap, If the service is good, then the tip is average. If the service is excellent or the food is delicious, then the tip is generous. Now, please understand, these rules can be constructed from this toolbox, and I'll show it to you in just a second. Basically, if and these conditions, actually these rules will be constructed using the toolbox, and then you can actually have an outcome. Now, what that means is once you click, okay, then finally, what you have is you have the interpretation of the tip. So if so you can see that the tip could go from 0 to 30%. So mean the sort of cheap is 5%, average is 15%, and generous is 25%. So this is basically the membership function. And then what you can do is you can look at the surface, and this gives you that fuzzy logic surface. So now what you can do is you can actually go to the quality of the food, you can go to the quality of the service, and this can give you the value, the percentage tip that you should ideally be offering. Now, the beauty of it is the human knowledge is encoded into those linguistic rules. So we have used our abstract knowledge to write an algorithm, and that is where the fuzzy logic shines. Now, the story does not end here. What I want you to understand is once you are done with this, the fuzzy logic designer will allow you, to export the code, which is the whole logic that you have written can be exported as a MEX. It's a C. You can write, MATLAB will write a C code for you that actually would implement this algorithm. So what would be the input to that C code? The input to that C code would be just two numbers: the quality of the service and quality of the tip. Quality of the service and quality of the food. And then that C code will take those two inputs and provide an output. Now, there is another way of doing it. If the fuzzy logic is simple, then what you can do is you can actually create a lookup table based on this. So for an example, for each value of food and each value of service for X and Y coordinate, you can specify the value of Z. So basically you can create a lookup table, and microcontrollers can implement lookup tables very quickly because those can be implemented at the pointer level. So you can have a lookup table. Another approach is, since now you have this surface, you can implement some type of a surface fitting algorithm that will give you an approximate equation of the surface. And then you can generate that equation using some type of optimization routine, and then use that equation to determine the tip based on the quality of the food and the quality of the service. So this is exactly how the fuzzy logic works. Now, what I want to do is, the later part of the session, I would like you to go to fuzzy logic toolbox. So fuzzy logic designer. So if you have fuzzy logic toolbox, then this will come up. You can see this fuzzy logic designer. Once you know what your inputs are, what you can do is you can actually add the membership functions. Then you can decide the boundaries of the membership functions. You can decide the shape of the membership functions. Then you can decide the way that your output needs to look like. And then here you can actually add the linguistic rules. So let me try to. So everyone, have you opened this fuzzy logic designer? Okay. Now in fuzzy logic designer, so there are two types of fuzzy logic inference networks. There is something called as Madnani fuzzy logic, and there is Suro fuzzy logic. And again, both of them have their advantages and disadvantages and applications. But I just want to talk about this simple algorithm. So what you want to do is you can go here and then say file. Here you can choose the different type of fuzzy logic algorithm. You can use Mamdani or you can use Sugeno, and then basically add. So so what you can do is you can actually go to this input. Then you can actually change the name of this input. So you can say maybe food. So now this will be food. Actually, I would say bad food. Bad food. I would say okay food. And then I can say good food. So this is, so now you have these three membership function. You can interactively drag the boundaries. So if you want, and you should be able to move this. And then what you can do is you can go to, and then here you can actually decide the binary rule. If the bad, okay, let's go to the output. So I'm gonna say low tip, medium tip, and then last one is high tip. So now you have these three, and now when you go here, you can actually if the bad food, your low tip. So you can just click add, and now can you see that that binary rule got implemented? If the food is okay, then the tip will be medium. So you can actually say add rule. If the food is good, then you can say, then the output is high. So add rule. So this is how you will construct the fuzzy logic code. Everyone understood this? And then if you want to add one more input, just double click, and then you can add one more input. If you want to change the output from one output to two outputs, that can be done. And then basically, once you construct this fuzzy logic algorithm, you can actually, if you want to add variable, say I'm going to add input variable. So I would say this is food. So I'm going to call this variable food. I'm going to call this variable service. I'm going to call this variable food. They close. So I don't know why it didn't. Okay. So I think we will have to change here. Okay. Here I have to change this to service. So now I have this food service. I go to output and then change this. Now I constructed, I look at the rules. So I got service, I got food. Okay. So where did my so, and then what you can do is you can actually generate the surface. So this is how you will construct the fuzzy logic. And then what you can do is you can take this file, export to the workspace, and then workspace variable you can construct. So you can see that this becomes a fuzzy logic object that you can import, use in Simulink or any other code that you are using, and that will actually can be used to control maybe a robot or to fuse the sensors, accelerometer, gyros, or combine data based on the LiDARs and the IMU or some odometry. So this is how you would use the fuzzy logic. Any questions here? Any question on the fuzzy logic? Okay, so let me stop sharing. Any questions from my online students about the fuzzy logic? So again, I just wanted to give you an introduction to fuzzy logic, because clearly fuzzy logic can be applied to different cases. Now, what I want to do is, I just want to discuss some theory part that is discussed in the textbook. So bear with me for a second. Me get my Zoom setup. So what I want to, yeah. Any questions? Well, it completely depends. Fuzzy logic, when I started working, the microcontroller and computation power was not as high as what is today. So at that time, we had to do some tricks. But nowadays, with the current microcontrollers and microprocessors, I don't think fuzzy logic implementation is that computationally intensive. So just bear with me for a second. Let me okay. So what I want to do is, I want to quickly go through the textbook, the information that is given in the textbook. So we talked about the fuzzy logic. In this chapter, the fuzzy logic is discussed in the context of robotics. So for example, if you have some type of a linguistic rule, like robot picks up a small component, moves it slowly till it is pretty close to other component, and then basically it moves fast or it moves slow. So these linguistic rules can be incorporated in some type of algorithm, which can be well described by fuzzy logic. So for an example, this words like small, slowly, relatively fast, some force, almost aligned, that are easier for us humans to interpret and understand, but very difficult for computer to understand. So what we want to do is we want to take these fuzzy statements and convert those into some type of algorithm. And clearly the robots understand the crisp thresholds. Either it is on or it's off. So they don't understand it could be on, it could be off, that type of stuff. So what we want to do is there is concept of fuzzy sets that we talked about. So we talked about the membership functions. We talked about if if you have an instant wherein you could be part of one set and also the part of other set, you could be partially in one set and partially in other set. So there are different sets that you can play with. Typically, you would have some linguistic rules which will actually be developed by humans that will have some type of if, else, then type of rule. Again, that will be dependent on the binary logic. Then the idea is you take the crisp input, do the fuzzification, find the fuzzy variables, feed that fuzzy variables to the inference mechanism. From the inference mechanism, you get fuzzy output and you do the defuzzification to get the crisp output. So again, fuzzification is converting crisp to fuzzy. Then membership functions that we talked about could be the relationship between the variation in the variable and how is that part of that set. For an example, if the value of the variable is somewhere over here, that clearly indicates that that value is completely in this set. If the variable is somewhere over here, that means this variable partially is in this set. And you could have multiple membership functions that are overlapping. So certain value could be 0.2% in one set, 0.8% in the other set. You could have different different functions that actually allows you to have crisp boundaries, fuzzy boundaries, varying boundaries at I mean, you can manipulate the edges, so on. You can have different functions. You can have Z-shape or S-shape membership functions. In case if you are looking at S-shape, it is similar to what they use in neural network. So basically, then you can have an example of a membership function, wherein as you can see that there are 1, 2, 3, 4 membership functions. So basically you have this speed, and what you want to do is you want to characterize whether someone is driving slow, is driving fast, is driving medium, or is driving very fast. So depending upon how you perceive, you can have a varying degree of membership. Then what you can do is you can add the rules wherein you can say that if else then type of statements, and as I showed you in the fuzzy logic designer, you can use inputs and construct those rules. You can add the binary logic and an or. Again, you can actually construct some type of flow chart or a block diagram if you want to. And then what you do is you basically do a defuzzification, which means you get the output from the inference system, and that output from the inference system is mapped to the crisp result. There are two techniques that are used, and I talked about these techniques briefly in last class. One classic technique is the center of gravity method, which means again you look at the weights and then multiply those by the membership functions, add those and find where the centroid is. So where is it mostly located? And then you can have this Mamdani's inference method, wherein again what you do is you truncate the output and then basically add the remaining truncated values and then look at the shaded area and then calculate the center of gravity. Again, there are different rules, but this one is a very commonly used. That's why the fuzzy logic network that we talked about talks about Mamdani network, because this is how that rule is implemented. If you want to simulate, I would encourage you to use the MATLAB fuzzy logic toolbox that I showed you. And basically in that toolbox, you can actually have the input variable, then you can have the threshold speed, and you can add the output variable as resistance. So, and then as you can see, you can construct a very complicated sets of fuzzy logic. Now, again, believe it or not, I don't know if you have seen this problem, wherein what you have is you have a horizontal card, and then you have a vertical pendulum. And this card can move forward and backward, and there is a motor over here. And then you want to vary the torque of the motor so that this pendulum stays upright. So what you can do is you can construct the fuzzy logic rules based on your linguistic interpretation and then implement the controller. For an example, if the cart is going towards right, and if the pendulum is going towards right, if I want to make it upright, then clearly I want to apply the counterclockwise torque. Depending upon how fast the cart is going or how fast this pendulum is falling, I need to increase the amount of torque. So please understand these, our interpretation, what we understand from the physics of the problem, the rules, computer does not understand. But fuzzy logic would allow us to encode these rules that we can think about, that the knowledge that we have into some type of algorithm. And depending upon number of states, the algorithm could become very complex. But please try to understand with MATLAB toolbox, it's very simple. You just click and add those rules. And then at the end, what you have is you construct this surface. And once this surface is constructed, basically you can use that code on the embedded software, or you can just use some type of a curve fit to get an equation, or you can use a lookup table, and this code can be flashed onto the microcontroller to basically program the robot. And these are the implementation strategies. We choose input outputs, look at the fuzzy sets, assign names, develop the rule base, simulate the system, then modify the system if needed, and finally you can use that fuzzy logic algorithm to control your robot. And with that, we are done with chapter 12. So at this point, I'm happy to announce that we have completed robotics 1, and hopefully I will see you all in robotics 2. The material that we discussed in this class is very important if you really want to become a roboticist. So I would encourage you to preserve the notes and refer to them as and when needed. And also the textbook, Saeed Niku's textbook has wealth of information, and we have completed all the 12 chapters from that book. So it was an honor and pleasure teaching you all, and I hope you enjoy the course. Thank you very much. So, but at this point, I will be happy to answer any questions you may have. Don't forget to finish all the projects, assignments, so that I can post your grades by next week.